All right, welcome back. Let's continue with our recursion slides. So, the last thing that we talked about last time was the Fibonacci sequence. We came up with a recursive function that told us the nth element of the Fibonacci sequence, so we needed to make two recursive calls to make that happen. And there were also two base cases, which was really cool. There was an issue, though. So let me bring in the code from last time. Let's see. Lecture 21, fib.cvp. Let's copy it into here and let me do some stuff with it. I'm just going to print out every time fib of whatever is being called. Calling fib of, and then I'll type the n. Okay, so it's just going to tell us when fib of whatever gets called. Not a big deal. And so then I'm calling fib of 7. Okay, watch this. Dun, dun, dun. Fib 765432110, cool. But look at what happens. 5432110, then it's calling fib of 1 again, then it's calling fib of 2 again, then it's calling fib of 1 again, what? Then fib of 0 again, then 3210, then 1, then a lot of weird stuff is happening. A lot of duplication is happening. What is this? Let's talk about that. Okay, so sadly, we're repeating a lot of work. Fib of 5 needs to call, if you think about it, fib of 5 is going to call fib of 4 and fib of 3, asking for what those Fibonacci numbers are. Let's try and make this as wide as I can. It's going to call fib of 4 and fib of 3. Fib of 4 is going to call, well, it needs to know, it needs to sum up fib of 3 plus fib of 2, right? Fib of 3 plus fib of 2. This is just fib of 5, by the way. And then fib of 3, that needs to call fib of 2 plus fib of 1, right? It's the two previous elements. And then fib of 2 needs to call fib of 1 and fib of 0, right? That needs to happen. And then fib of 2 needs to call fib of 1, fib of 0. Fib of 1 is a base case. These are also base cases. And then fib of 3, again over here, needs to call fib of 2 to add it to fib of 1. Which this needs to call fib of 1 plus fib of 0, and I didn't give myself enough room. So, do you notice anything? And then finally, all these are the base cases. No extra work needs to be done there. But, oh man, look at what's going on. Fib of 3 over here, we have to do all this work over again, though fib of 4 also needs to compute fib of 3 over here. The same computation is being duplicated over here. Do you see that? That's crazy. So essentially, every time you make a recursive call, like to fib of 4, for example, it's got to do twice as much work, essentially, as fib of 3 would have done. Fib of 5 needs to do essentially twice as much work as fib of 4 would have done, because here's how much work fib of 4 is doing, and then you also have to include this side. Crazy. Almost double as much work. That's a ton of repetition. And then fib of 2, look how many times we're trying to compute fib of 2. Over here, over here, over here. That's duplicated that many times. And don't even get me started about how many times we're computing fib of 1. Fib of 1 this many times, fib of 0 this many times. It's just, the lower the number, the more duplicated that work gets. That's crazy. Why are we doing that? We could have saved all that work and just, like, done fib of 3 once and for all, right? But that is not what's happening secretly. So that's no fun. So this is why I had this line from the previous slide, okay? It's a slow calculation because the bigger Fibonacci number you try and calculate with this method, it kind of blows up, okay? This is fine. But fib of 8 is doing twice as much work as fib of 7. Fib of 9 is doing twice as much work as fib of 8. If I try to calculate the 100th Fibonacci number, watch. It would actually take more time Oh gosh, let's not print out this anymore. That's going to be a lot of printing otherwise. So it calculates fib of 7 just fine, and then we're waiting for fib of 100. Well, let me just tell you that it's not going to finish in the amount of time that the universe has existed. It's that much work that is being duplicated that would need to have been completed in order for fib of 100 to be calculated. That's how much extra work is being done. Whereas you could calculate this very quickly with just a normal like for loop. This will never finish. Okay? So there is a difference. But at least it was very easy to come up with this recursive function. It makes a lot of sense given the way the Fibonacci sequence works. Okay? So that's my example of Fibonacci. Recursion isn't always the best solution to a problem, but sometimes it is. Okay? So let's go back to some simpler examples now, just to get recursion ingrained in our minds. So let's do this example. Let's print from 1 to n in order. So for example, this is going to be the function's signature. It'll take a number. That's what we want to print from 1 to. And so we call print from 1 to, and then we give it 5. What's supposed to happen is on the terminal screen, it will print 1, 2, 3, 4, and 5. Right? 1, 2, 5. That makes sense. This is a recursive problem, though. Why? Do you see it? Do you see the smaller print from 1 to problem within this problem? Here it is. You can print from 1 to 4 first. That's a smaller print from 1 to problem. And then you can print your 5. Isn't that nice? So here's the recursive case. You recursively first print from 1 to n minus 1. And the beauty of recursion is you get to just assume that this does the right thing because it's the smaller recursive call. Assume this works. So with this example, let's just assume it just printed for you by making the recursive call, the numbers 1 through 4. What do you have to do to build up the final solution? You just need to worry about printing your 5. So you just print that n to solve the bigger problem. That's the recursive case. And then the base case is, well, when do we have no more work to do? You can think about it this way, like, I need to print from 1 to 5 using my recursive case rule. When is there no more work left? So like here's this one, recursive call to print from 1 to 3, which will make a recursive call to print from 1 to 2, which will make a recursive call to print from 1 to 1. Technically that could be your base case. To print from 1 to 1, you just print the number 1. But you could go even further. You could be like, let's print from 0 to 1, which is nothing, and then print our 1. Okay, so there's like a nothingness case inside of this, and that can be our base case. So if n is 0, how do you print from 1 to 0? That's kind of like going backwards. There are no numbers between 1 and 0 in that order, so you can just print nothing, and that is a valid base case. Isn't that cool? So that is going to be our first example. Print from 1 to 2. Let's do that. So we're going to call, I don't know, print from 1 to, and then give it 5. And remember the signature, it looks like this. It takes a number n, and then we need to figure out if in the recursive case or the base case. So if it's the base case, that means n was 0. We print nothing at all, so I guess I don't even need a body. Otherwise, we're in the recursive case. We need to recursively print from 1 to a smaller number. Print from 1 to n minus 1. And that's just a call to this. You get to assume that this actually is going to print from 1 to n minus 1. And then you just have to worry about building up the final answer correctly. The last thing left was to print your n. That's the full solution. Okay? And so that is the recursive function to print from 1 to a certain number. Yay! And so we got 1, 2, 3, 4, 5 perfectly. And this is how you do it. So let me prove to you why that's working. Let me go back to the stack example. This is always important as we're first learning this. So main called print from 1 to 5. So I'm just going to call the function p. So we called p of 5. And p of 5 is like, okay, I will eventually print my 5, but only after first printing from 1 to 4 recursively. So we call p of 4. Still haven't printed anything yet. Like here's the terminal screen. P of 4 is like, oh yeah, sure, I'll print my 4, but only after I printed from 1 to 3. So it calls p of 3, which we'll call p of 2. I think you get the idea, which we'll call p of 1, print from 1 to 1, and then p of 0, print from 1 to 0, makes no sense. That's the base case. We do nothing, and it just returns. And it's like, okay, cool. Now every other function gets to do what it was meant to do. It's like, okay, we come back to print from 1 to 1. We just printed from 1 to 0. That returned. Now we can print our 1. So p of 1 prints its 1 and finishes. Cool. Then we're back here in p of 2, waiting to print from 1 to 1. We just finished that. Now we can print our 2. Now, everybody's waiting on this line to have it complete so they can print its n. N is 2, n is 3, n is 4 in all of these cases. So p of 2 prints 2. P of 3 finished with the recursion prints 3. P of 4 finished with the recursion prints 4. And then p of 5, again, waiting to print from 1 to 4. That's finished. Now it prints its 5. And it's done. And that's why it prints from 1 to 5 in that order. Okay? Please yell at me if this is not making enough sense. This is the kind of example that comes up a lot. Okay? This is good practice with recursion. All right? Finding a problem inside of itself. So that's my example for you. I want you to try and do something different, but very, very similar. So try to, on your own, come up with a recursive way to print from 1 to n in reverse order. That is, from n to 1 instead this time. Okay? So I want you to draw what p of 5 would look like, first of all, and then I want you to see if you could find where that smaller recursive call needs to take place. If you can't get the full code, try and think about the strategy. Like, how would you write down the recursive case and the base case? Okay? This is a great thing to pause and ponder. So we'll come back and I'll talk about my way when you have spent some time on this. Okay? So, what were your thoughts? So what does p of 5 look like? So p of 5 is supposed to do what? It's supposed to print on the terminal screen 5, 4, 3, 2, 1, right? In reverse order. So what is the smaller recursive call? It prints from 1 to n in reverse order. That's what it's supposed to do. That's what this problem does. So where is the smaller printing from 1 to a number in reverse, or print from that number down to 1? Here it is, isn't it? That's the next smaller problem. That's p of 4. That's print from 4 to 1. And now, this makes a lot of sense. Where is the smaller recursive call? Do you see the difference between this version and this version? The first thing you needed to do in this example was make the recursive call, because that needed to happen first. We needed to print from 1 to 4 before we printed our 5. But look what needs to happen here. We need to wait to print from 4 to 1, don't we? We need to wait to print from 4 to 1. We have to print our 5 first. Crazy. So that's the only real difference. And that makes a big difference, okay? So let me show this to you in reverse order. So this is now the recursive case. Instead of recursive call print, it's print your n and then recursively print from n to 1. Isn't that cool? So yeah, this was, let's see if I can copy all this. This was p of 5, this whole thing. Oops. Let's go back to blue. And here's the recursive call. Here's printing from 4 to 1 in reverse, right? So what needed to happen first? We needed to call cout first. We needed to print our n first, because the 5 needed to appear first, and then we could throw off the rest of the problem to the smaller sub-problem. Okay? Print recursively from 4 to 1. Is that what you got? That's the trick. And then the base case can be, okay, you get down to here, boop, 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 boop. You can just do nothing when n is 0 again. That's totally fine. Okay? That's the idea. So let me keep these in the same file, actually, because it's going to be interesting. Print from 1 to, and then let's be like, I don't know, How about reverse at the beginning? Reverse, print from 1 to. And you gotta remember to make the recursive call to the correct function. So that's the name of the function now. And the only difference was, instead of recursive call first, then print n, it was n needs to get printed first, then the recursive call. That's the only difference between these two functions. This order controls whether or not you print in order or in reverse order. Isn't that cool? That is all you need to do differently. So let me show that to you. And yes, that one prints from 5 all the way down to 1. And we noticed that we needed to make that recursive call solve the smaller problem after we printed our n. Okay? That's the only difference between these two functions. So this is a great example to study. Okay? And we noticed when that recursive call needed to happen, when that smaller answer was needed, it was after we printed our number. Okay? That's how that works. So that's a fun little example or sequence of examples. And I just have more for us. Until it gets ingrained in our minds, I just have a ton of examples of recursion. So here's my next one. Let's print the characters of a string in order. Okay? Let's talk about this, because this is going to come up later. This is a common thing to want to do, to iterate through something, just like we would use a loop for, but we can use recursion for it. Okay? So, all right, let's talk about this. Let's say that we have a string s, and maybe it's like has the word blah stored inside of it or something. It's some string. Here's blah. What do we need to do? We want to print the characters of the string in order. So maybe we want to print it like B, then L, then A, then H, each on their own line. So now, what we have to do is come up with a base case and a recursive case. Usually the recursive case is like the easier one to do first, but the base case for this example might be the easier one for this particular case. So if you want to print all the characters of a string in order, what's the string where you have nothing to do, where there are no characters, right? You need to find a smaller string to print in the recursive case, because we're trying to solve this problem in terms of itself. When is there no smaller string? When is there no fewer characters? That's when the string is empty. So that is a perfect base case for us. When the string is equal to the empty string, then we do nothing at all because there are no characters to print in order. So that's definitely our base case. And then we have to worry about our recursive case. So the question is, how do we want to break down this string? Because we need to find a smaller string to print its characters of, right? Because we're trying to find a subproblem here. So the question is there a smaller string here that we could print out inside of this string? And the answer is yeah, there's plenty. Here's a smaller string. Here's a smaller string. Like there's a bunch in the middle over here. They're all smaller strings. Usually you care about the next smaller string, and so these two are your normal options. And for reasons, let's choose this one. Let's break down the string into the first character and then the rest of the string, okay? So that's the one we're going with, first character and rest of the string. And so we're going to make a recursive call on LAH and assume that that will print the characters of that smaller string LAH in order. And so that's this, just like that. So we assume that a recursive call is going to take care of that. And then our bigger solution needs to worry about printing this B. When does that B need to be printed? Before or after the recursive call? It's before. You see that? So it looks like the recursive strategy is print the first character of your string, and then recursively print the smaller string. Everything but that first character. Okay? But because of the way that you can break down a string, you could also break it down into the last character and everything but the last character, for example. There are multiple correct recursive cases. Okay? That's the idea. So let me show this to you. Print the characters of a string in order. So let's say I need strings. And then I want to, I don't know, print chars of the string s in order. Okay, so this is the function that I'm about to write. And it's going to take a string s, and let's see what we need to do. We need to, well, figure out if we're in the base case or the recursive case. If we're in the base case, we have nothing to do. If s is the empty string, do nothing. I could say return if I wanted to. In a void function, if you just say return, it just stops and gives back its answer of nothing to whoever was calling it. Else, we're in the recursive case. Technically, I don't have to say return here because there is nothing after this if statement, but I will include it for fun. Else, recursive case. We need to print the first character and then recursively print the smaller string. So let's do just that. How do we print the first character of s? We can be like cout s at 0. That's the first character. And then recursively, we want to print the characters of that smaller string. So s, but s with everything but the first character. So there's plenty of ways to do this. You could erase the zeroth index character. You could maybe take the substring of this string starting at 1. And so this will get the next smaller string. Okay? This will chop off the 0th character of s and get everything but that character. Okay? Make a substring out of it. And if I leave out the ending index like I am, it'll just go until the end of the string. Okay? So that's one way to do it. Oops. And we have our blah. Yay. Okay. So that is how we can do that. Now, let me have you try something, I think. So that is that example. Let's see what I wanted to do next. Okay, maybe we can do this one first, and then I have an example for you. So let's now try to print the characters of a string in reverse order. How might we do that? Oh man. So let's see. If this was our s, and we had blah. Well, what are we going to do? Let's, again, break down the string into the first character and everything but that character. So first character and the rest of the string. And we need to output this somehow. We need to output, instead of blah in order, we need to output HALB. So where is the recursive call? What's the recursive case? Because here's the smaller string. Here is the smaller string reversed, right? So it looks like the very first thing we need to do in the recursive case is to recursively print the smaller string backwards. That needs to happen first this time, because that's the first output. The output needs to come from not our first character, b. b waits until that's over. Okay? That's the idea. So first we recursively print the smaller string backwards, and then we we just print the first character, sorry. No recursion involved for that one. Okay? So base case is the same. Still, how do you print all the characters in reverse order of the empty string? Well, you print nothing at all. It's just the recursive case that has changed. So let me show you this. Print chars versus print chars reverse. And remember to call the correct function. Boop. The only difference was recursive call first, then print our character. And that makes all the difference. So again, the only difference was that recursive case, the order of the printing versus the recursive call. That gave us reverse print a string. So pay attention to when that recursive call needs to happen. When do you need the work from the smaller problem? All right, now here's something that I want you to try. Try to come up with a recursive algorithm to capitalize a string. And all I need is pseudocode right now. Don't try and write this yet as real code, but come up with the way of doing it, okay? So think about, like, what is it going to look like when you call your capitalize a string function that is recursive, like this is your problem, call it p. What happens when you call it on the string containing blah? And then, like, what does the smaller recursive call entail? Where is it? What order does it happen in? Things like that. So come up with that idea, and then I'll show you my thoughts. So, again, here's the string. How might we do this? What we want to have happen, right, is to change everybody. Change this to capital B, capital L, capital A, capital H. And we can use the same pattern as before. We can break down the string into the first character and the rest of the string. And now let's think about the base case and the recursive case. Again, the base case could be the empty string because there's nothing to capitalize when there aren't any characters. Now in the recursive case, things get interesting. Let's talk about it. Recursive case. What needs to happen? We need to capitalize the first character, right? Because we're breaking it down into the first character and the rest of the string. We need to capitalize that first character. And then we need to recursively capitalize the rest of the string. That's the recursive call. That's the smaller string. We can use the same problem we can call ourselves to solve that sub-problem, right? So recursively capitalize the rest of the string. All right, and the beauty of this is this order doesn't matter, actually, for once. In some order, you have to do this. Because we're going to take the string by, like, reference, so that we're modifying it in place. And so as long as, by the end, this has been capitalized and all of these have also been capitalized, all those characters, then it doesn't matter if you capitalize the smaller string's characters first or your original first character that you're leaving out first. Okay? So in some order do this, and either way will work. Isn't that neat? So that is a good strategy, I think. And let me show you how to do it, not for normal strings, not for C++ strings. Let me show this to you for C strings, because those are the other kinds of strings that we know about. So let me show this to you. So now the string looks more like this, right? It's always an array of characters with that special null terminator character. It's always, it'll look like B, L, A, H, and then null terminator character. This needs to get transformed into capital B, capital L, capital A, capital H. Same null terminator character, though. And again, we break it down into the starting character and the rest of the string. That's the goal. So yeah, again, this is our recursive case. You capitalize the start of the string. Let's just do it in this order. And then recursively capitalize the smaller string. That is the rest of the string after the first character. And then we've already had our base case in mind. What's the string that doesn't have to have anything capitalized? It's the empty string. So that's when it's completely empty. It just contains the null terminator character. Yeah. And that is almost the answer. It gets a bit fancier when we talk about what C strings are, though. Because remember that a C string is represented as a pointer to the first character of it. So really, if like our string was this, like char star S, I guess S2 this time, if it was ABC, really, this is what's happening in memory. And this will help us come up with our answer. Here's A, B, C, null terminator character. S2, the name S2, is really a pointer to the first character of the string. It's pointing to the A. Maybe this is address 100, so it holds 100. Isn't that interesting? And then the rest of the string is +1 because it's the string starting at the next character. This is S2 plus 1, I guess. That will give us address 101, which will point right here. That's the rest of the string. Does that make sense? You can actually give it a name if you'd like. Just be like S2 rest. But it's represented as a pointer to the start of that smaller string, which is a pointer to the character right after the original string. That will give me the BC. Do you see that? That's the smaller string in terms of a C string. The smaller string is the string's address +1. Isn't that cool? So that is the next algorithm that I want to show you. So it's this idea, but getting a bit fancier in terms of pointers because of the way that C strings are represented. Okay, so let me show you this to you. Oops. We want to do it this way. So capitalize.cpp. So now I want to have a C string. So char s equals blah. That's one way to declare a C string. Okay, and then I want to be able to call capitalize on it. Yes? And then I want to print the string back out. See how it knows how to print C strings too. And here's how it's going to work. So it's void capitalize, and it's going to take a C string, and we're going to pass it by char star. Okay? So stir is a pointer to the first character of the C string. That's what it means to be a C string. You're giving a pointer to its first character. And so now our job is to figure out if we're in the recursive case or the base case. Are we the empty string right now? If so, we have no work to do, nothing to capitalize. So if, and let's include C string and CC type, because strlen is a function on C strings. If the length of the string is 0, that means it's the empty string. Do nothing. That's the base case. Otherwise, the string has some positive length, in which case, let's capitalize the start, capitalize the first character, so use the string as an array, like it really is. Stir of 0 equals 2 upper stir of 0, and then we will recursively capitalize the rest of the string. So the rest of the string is stir +1. Do you see that? This is a pointer to the start of the rest of the string, one character from the start of the original string. That is pointer arithmetic. So if this was, pretend this was stir, this is stir +1. It's a pointer to the start of the rest of the string, a pointer to the next character, because C strings are pointers to their first characters. Isn't that cool? And so this is how you pass the rest of the string. Just the address of the starting character, one after the one we were originally given. All right, so let's see how that's working. And what do you know? It's going to capitalize the entire C string. And again, the order of these two lines does not matter because we're going to visit every character one way or another. Okay? So that's another fun example. And then I have saved my last, fanciest programming example for the second to last slide. Okay? This is going to be a fun one. So let me talk to you about how to scramble all the characters of a word. This is a recursive problem, and this is actually one of those problems that is much easier to do with recursion. Like, try to think about how to do this with a bunch of loops. It will not make any sense at all. The only way to think about this problem is with recursion. And so I will try and convince you of that now. So here's our goal. We would like to create this kind of function. It's going to take a string, and we would like to permute every possible character in that string. We want to find every possible permutation of characters of that string and give back every possible option as a vector of strings, a vector of possibilities. Okay? So if we call it on, we call perms of the string ABC, for example, what we want it to give back is a vector of all the possible permutations of the string of characters ABC. So that is, of course, including ABC. Then we also have ACB. And then we have, let's see what's next. Well, then it's BAC. And then BCA, right? And then C could also come first, CAB and CBA. There are 6 possibilities, 6 permutations. It's 3 factorial, right? If you remember that rule. That's the idea. And then that is what we want to give back. And let's talk about the recursive case. Where is the smaller word scrambling problem, given this idea? We want to find the permutations of a smaller string and use that to build the permutations of this bigger string ABC. Let me show this to you. So here is the idea. Here is A. Just put A first. And then these two are all the permutations of the string BC. Do you see that? Here is the character B. Just put that first. And then here, after the B, here are all the 2 different permutations of the string AC. You have AC, or the C could come first and make it CA. And then finally, you have this character C and all the permutations of the 2 characters A and B that come after it. That's a smaller permutation problem a bunch of times. Do you see that? I'll try and prove that to you when I code it up. And then, let's talk about the base case. When is there nothing to scramble? Usually with strings, it's the empty string. That is always your base case. So, what are all the permutations of the empty string, all the characters in the string that is the empty string? Well, it's nothing. Or I guess there's the single permutation of the empty string itself. Yeah? That's the base case. So, this is the recursive case now. With this idea in mind, here is how you calculate the permutation, all possible permutations of this, of the characters of this original string. What you do is you pick a starting character. You have to try them all. You have to be like, okay, you have to give everybody a chance. Like A could be the starting character, B could be the starting character, C could be the starting character. And so we do give them all a chance. Here's A, here's B, here's C. And so let's pretend like we choose A. A is the starting character. Then we have to recursively scramble the remaining characters. So if we choose A to scramble, then the remaining characters are B and C. So we'll scramble now the string BC. So we want to make a recursive call. And that's going to give us back the vector containing BC, right? We get to assume it's going to do it because it's a recursive call. It's going to give us back BC and CB. And then our job is, well, how do I build up all the permutations of these characters with A at the front? Because this was supposed to be our starting character. You just plop it at the front of both of those permuted strings. Isn't that cool? And so the final output for when A is at the front is all of these strings. It's ABC. You took that one, put an A at the front, and ACB. You took the second permutation, and again, put an A at the front. And you do this for every possible starting character, okay? So pick a starting character, recursively scramble the remaining characters, and then build up your result vector based on taking that character that you are saying is going to come first, and then put it at the start of all of those permuted smaller characters, okay? And then after you've tried everybody, you have one big vector containing every possible permutation. Isn't that cool? This is definitely the hardest problem. I'm never going to ask you to do something this fancy on a test, but this is a very, very exciting example. It's a case of like, how in the world would you do this without recursion? It's pretty much impossible. Okay, so let me show this to you in code. Or I guess we're calling it perms, so let's just keep it like that. We're going to use normal strings again. So it's going to be this function signature. And so I guess I need vectors too. And so here is what's going to happen. So again, we need to figure out if we're in the base case or the recursive case. So if, I don't know, s is equal to the empty string, that's the base case, then we want to return the empty vector, or sorry, the vector with just the empty string in it. Okay? So a vector with just the empty string in it, that's what we give back. That's how you permute every character in that string. Cool. And then otherwise, we're in the recursive case. So we have to build up again a vector of strings that is our result. And based on this, we have to fill it. So we have to try every possibility, try every character in S. Pick a starting character. We have to try all of them. So that means we have to iterate through this string, right? Try A, try B, try C. Yeah? So pick a starting character, and we have to try them all. So let's do this as a loop. For I equals 0, I is less than s dot size, I plus plus. That's the index of the character that we want it to start with. So pick a starting character. That is going to be, oops, that's s at I. Okay, so the first time it's going to be A, the second time it's going to be B, the third time it's going to be C for our example. If we call it like this, terms of ABC. And then we want to recursively scramble the remaining characters. So we're going to call perms on every character in this string S except for the one that we just picked out. Yeah? So for example, if we picked the B, we want to get rid of the B and only consider the string AC to permute now. We need to do that. So we need to remove the character. Okay, so we need to do something like this. Smaller string equals S, but it's S with index I removed. Okay? So here's one way to do that. Smaller string dot erase, and then you give it index I, and I want to erase one character from index I. So this will erase that ith character. Okay? Definitely ask me about this if you're interested. This is a fun, in-depth example. And then we want to permute. We want to find all the permutations of that smaller string. And remember that this will also give back a vector of strings, every possible permutation. Okay. So now we've done the scrambling. Now we just have to add the starting character to every permutation of smaller string perms. Yeah? And then to the start, right? To every string in smaller string perms, and then we want to add that to our result. This result vector that we're trying to build up. Okay? So here's how we can do it. For, I don't know, let's just say string, smaller string perm in smaller string perms, go through it and create the string that consists of taking that starting character and putting it at the front of that smaller string perm. This one that I'm getting out of this vector. And that's the one that I want to add to our result. So for example, I just put A at the front of BC and CB, and I'm pushing these two strings to my result vector now. That's kind of fun. So once I've done that, I've given every starting character a go, I can return my result vector. And so this is definitely a very in-depth example, a good one to study and ask questions about. Okay, so let's see how horrible of a job I did on the first try. So let's try and print every option that we got back out of that. So for string s in p, let's print s. And let's see how good we did. Do we have 6 options? Oh yeah, so it is working. Good, good, good. So yeah, base case, you give back the empty vector, or the vector with just a single empty string in it. And in the recursive case, you gotta pick a starting character, recursively scramble the remaining characters, there's the recursive call right here, and then add that starting character that you were saving to the start of all of those permuted smaller characters, and that's the thing that you add to your bigger answer. Okay? That's the full-size string again with every single character in it. So ABC, ACB, PAC, BCA, CAB, and CBA. And this definitely blows up for bigger strings. So like if you add a D, now there are 4 factorial options. 24, right? And it's still working. So definitely study this code. Ask me lots of questions about it. But that is my fun, in-depth example that, oh man, did this need recursion? Like, think about how you would have done this without making this recursive call right here. Because we just get to assume that it's going to permute everything properly. We don't have to care after we built up our recursive case properly. Okay, so that's scrambling the characters of a word. And then finally, let's see how we're doing. The final thing that I want to show you is not something I'm going to code, but I just want to tell you about this example because it's a very standard example with recursion. Okay? You don't have to understand any of it. I'm going to go fast. It's just a classic example that you may have already heard of actually, but I don't want you to miss out if you haven't. So this is called the Tower of Hanoi. It is this game. You have 3 pegs and you have a bunch of cylinders. That's a stack of discs, we say. And the object of the game is to move this entire stack of discs to this side, to this 3rd peg instead of the first one. But the rules of the game, the rules of the game is that you can only put smaller pegs, smaller discs on top of bigger discs. So like you could move this one down to here, and then this next one will be on top, but you can't put that bigger one on top of the smaller one. You're not allowed to do that. The only place that one could then go is over here. And then you could maybe put this one on top of this one, just like that. That's the game you have to play. Those are the rules, okay? And you can actually solve this game recursively. Here's how, okay? The base case is, there's a concept of the source peg, the intermediate peg, and the destination peg. Like this is going to be our destination peg usually. And here's the base case. You can move the smallest disk wherever you want because it's smallest. It can always go wherever you need it to go. Like it can go nowhere, or if there's something already there, I mean it's the smallest one, it can go on top of everything. So that's the base case. And then the recursive case is kind of cool. You get to move one smaller stack of disks. So everything but the biggest one. You can recursively make a call to move this entire stack of disks to the intermediate peg. So it looks like this. Boop, boop, boop. You can just assume recursion is going to give you a way to get here, to get from there to there. And then you're then able to, because this one's now by itself, to move the biggest disk way over here. And then you can again use recursion to move this next smaller stack of things all the way from this peg to this one again. And this time this one can be your intermediate peg. That is how you can solve the Tower of Hanoi problem with recursion. Please go look this up on the internet if you're interested. There are plenty of fun YouTube videos that explain exactly how to do this. It's a very fun problem. And again, it's one that kind of needs recursion in order to be solved efficiently. Like, you couldn't do this very easily with a loop, if at all. Okay? So these are the rules, and that is my quick example of another problem that kind of requires recursion. So feel free to look this one up. It's a very popular one, and you might see it again someday. Okay? So that is all that I have to say about these recursion slides. I would like to now go and release your next lab so that you have time to get started if you're finished with the previous one. So let me go and record that video now, and I'll see you there.